This is the 14th video in a course on single agent search. And in this video, we're going to be looking at some more details about how we can build alternate bounding functions for a best first search that does not perform node re-expansions. And so what we're going to look at is we're going to look at the requirements that were derived in the previous lecture or the previous video for avoiding re-expansions. And then we're going to look at some different functions that we could use that would achieve this. So if you remember, we had some requirements on what our guidance was. And so what we're going to be using is we're going to be using a search where we say f of n is going to be equal to phi of h of n, g of n. And what we want to look at and understand is what are the properties on the phi function here that I need to get things to work so that I can search and not have to do node re-expansions. And so over here, I'm going to write down what the requirements are, and we'll be referring back to these. So we're going to say, I'm going to use a capital delta here. So we have to assume that for some delta greater than or equal to 0, here are the requirements. So we're going to say is if I have phi of some x plus delta y, that must be greater than the phi of x and y. Okay, and so this says, so if you remember, x is going to be my h cost, and y is going to be my g cost. We see that there. And so that just says, look, if I increase the h cost, because this is what here I'm doing, if I increase the h cost, then my priority goes up, the priority value or my f value is going to go up. And therefore, I prefer a state, if the g cost is the same, I prefer one with a smaller h cost. So this one is a lower priority. We do go from low to high priority. And similarly, if I have x and y plus delta, it must be greater than x comma y. So similarly, that says the exact same thing. Before we said in terms of h cost, now we're going to say it in terms of g cost. So if I increase the g cost and leave the heuristic the same, then the state that I prefer is the one with lower g cost, because that's going to have a lower priority, and we go priority low to high. Now, if I compare between g and h cost, so if I have a choice of increasing my h cost, or I have a choice of increasing my sorry, I used the lowercase delta there. Let's change that. Okay, x plus delta, or I could increase my g cost. Then what I say is increasing my g cost is, in this case, so if I increase my g cost, then that's going to have a lesser impact in increasing my priority than increasing the h cost. And what this is essentially saying is just saying that the slope of this curve, it has to be something like this. So the -1 would be a 45-degree line, and we want it to be steeper than that. And so we expect to see some steep curve here, because what happens is if I increase in the h-axis, so this is g and h-axis, again, which corresponds to x, h does, then as I increase here, if we think about, if I can draw these straight, if we can think about isolines here, then we're going to go through lines a lot more quickly in the h-axis than I will when I move in the x-axis. And that's what this is saying. And basically, it's just saying I prefer suboptimal solutions. I can't be looking for solutions that are more optimal. They must be looking for suboptimal solutions. Okay. And then we need to ground these curves. So when we think about these lines that are being drawn, that each of them is associated with a priority value, and we're going to set what that priority value is. And it really could be anything, but we're going to ground it out. So what we're going to say is x comma 0 must be equal to x. And then, so that's going to say, you know, if this is 3, then this curve is going to have priority 3, and it's going to meet up here. And for the sake of this lecture, there's some more details in a 2021 paper. If I say 0, b of x, this should also be equal to x. So this curve that is coming here, if it's 3 here, then it's going to go to whatever my bounding function is. b of 3 here. Okay, so that's getting us our initial conditions, and these are ones that we're just assuming, and then we need one more condition, which I think is sort of akin to consistency of our heuristic. We need something like consistency of our phi function. So these are assumed. That these just are going to hold true. We don't necessarily have to assume this last one here, but as I said, I'm not going to get into those details. And then I require, given those assumptions, and this is given a consistent heuristic. There's a slightly different version of this depending on the consistency of my heuristic. But what we'll be looking at is phi of x plus delta, y plus delta. And I'm going to write it this way. I like thinking about it this way. So phi of x plus delta, y plus delta minus phi of x comma y must be less than or equal to 2 times delta. Okay, so the change when I go from a state x, y, I add delta to both x and y. So I add to the g and the h cost delta. Then it should go up by some amount, but the amount that it goes up must be less than 2 times delta. Okay. And given that, so again, this is review from the last video. What we want to look at now is what happens with bounding functions. So we're going to have bounding functions that are going to say what type of bound I'm looking for when I do my search. And so we have a w bounding function, b of w of x is just going to be equal to w times x, and b of gamma of x is going to be x plus gamma. So the w bounding function is a multiplicative. If I say 1.1, then I'm saying you need to be within 10% of the optimal solution. If I use gamma here, then I'm saying, for instance, 10, you need to be within 10 steps of the optimal solution. And what we're going to do is now we can look at so these are our bounding functions, and now we're going to propose some phi functions. So the first one we're going to look at is the traditional weighted A star, which is phi of h comma g is equal to g plus w times h. And if we look at this and we look at our conditions over here, what we can find is essentially what I've drawn here. And we can assume that w is greater than or equal to 1. And then all of these conditions here will hold. But it's actually this fourth condition, and I can number these 1, 2, 3, 4, 5, and then 6. Sorry, the numbering here is inconsistent with the last video because we skipped one there. But for the sake of this, we can number these 1, 2, 3, 4, 5, 6. And we check here condition 4, phi of x comma 0. So if we do that, we should get back x. And so x in this case is our h value. And so if I check this value that I have here, and what I want to say is phi, so let's try a real value here, 7, we can just say w is equal to 2 for the fun of it. Phi of 7 comma 0 is equal to, so g is equal to 0 plus 2 times 7 is equal to 14. And that should be equal to 7. And so we violated property 4. So it violates 4. So that's a priority function that under this framework, we're not allowed to use it. But notice here that these are all assumed that hold true. So we missed sort of our base assumptions. And what we just need to do here is we need to rewrite this function and in order to follow this. And so this is going to be our new weighted A star. And this is just going to say phi of h comma g is equal to g over w plus h. So by dividing everything by w here, we're going to actually fix all the problems that we had before. And let's just try this with the same values we did a second ago. So if we assume w equals 2, we can say phi of 7 comma 0 is equal to, now we have 0 divided by w, or 0 divided by 2. And so that's going to be 0 plus h of 7 is equal to 7. And so now that does meet condition 4 that we didn't meet before. And if we want to check the other condition, what we should see is phi of 0, comma. Now my bounding function says I could be up to 14 suboptimal. And that's going to be 14 divided by 2 plus 0, which is also equal to 7. Okay. So that's shown that both conditions 4 and condition 5 are met. And the last condition we want to meet is to check that if I add delta here. And so I did these numerically. Obviously, I could do these. We could just look at it and inspect it and discover this. But here, let's actually do this using delta. So what I'm going to get is, so I want phi of x plus delta. So this is going to be h plus delta and g plus delta. So g plus delta, and I'll go ahead and divide these out. So it's g over w plus delta over w plus h plus delta. That gives me my first term, and then I need to subtract just my regular term, g over w, and then I subtract h. And what I see here, what is this equal to? So my h's here are going to cancel, my g over w is going to cancel, and what I get left is with delta over w plus delta. And what we see here is that this is going to hold as long as w is greater than or equal to 1. Okay. So it says, look, I can't look for something, it doesn't make sense. I mean, it will run. I can run something less than 1, but you're basically throwing away your heuristic when you do this. And so it says I'm going to get this property of property 6 here, of this sort of consistency of the phi function, as long as w is greater than or equal to 1. And so that's good. Okay, so what we've shown here then is that this meets all the conditions, and this is a good one. Okay, so traditional weighted A star, we can't run that, but we can run this new weighted A star, and this is a perfectly good phi function, which is this piece right here. Okay, so now, this is interesting, and what we can do here, we'll do this for a bunch of these, is let's go back and let's take a look then at what happens when I use this for search. So we're looking here at an animation of a particular problem, and we'll look at this problem again and again. What we see on the right-hand side is actually our phi function. So this is for the best state in the open list. The line here, the diagonal, or well, the diagonal line, it's not is according to the slope that we're using. I believe it's 1.5 here. And we can see the states on here. And so as we run the search, which I'm going to do now, what we'll see is we see that we're equivalently basically sweeping this line across the state space. And as we sweep it across, eventually we'll get up to the goal. But all the nodes there are on the open list on the right-hand side, correspond to all of the states on the left-hand side. Now, when I made this video, you can see the open list is actually in green on the left-hand side. It's in red on the right-hand side. I haven't had a chance to fix this video, but in later videos, we'll switch the colors. So the open list will correspond on both sides. But we can see here weighted A star runs. It's equivalent to using this diagonal line. And then we find the solution that we find. And so now what we're going to do is we're going to go to a new function. And we're going to take a look at this, and we're going to develop our first piecewise function. And we call this a piecewise. So it's going to be piecewise xd, which is for convex downward. And for a little bit of history on this, there is a paper from 2019 that introduces a convex downward curve. And we call that convex downward parabola, which is called XDP. And this is a parabola that is connecting 2 points and with a curve. Of course, a parabola is a curve. And so it does that, and we get a very smooth bounding function that comes from that. The derivation is a little bit more than I want to put into this video. So you can look at the 2019 paper, again, by Jingwei Chen is the first author on that, and you'll see the derivation of that work and how the phi function is derived there. And so when you look at that, you'll see those pieces. And what we were looking here is, well, maybe we could do something slightly better than that. And at the end, I'm going to talk about, we'll actually see the performance of each of these curves, but at the end, I'll come and talk about, why does each of these curves have the performance that it has, and how can we understand what's going on. So we call this piecewise XD. XD is this convex downward. And so not a parabola now, but just a piecewise function. That is, convex downward basically means that the open part is facing upward. And I'll show you a picture of that just momentarily. So we're going to write this down. And this is a little bit more complex, but what we're going to say is this. And actually, this is a really interesting phi function. So this says that phi of h comma g is equal to, and I said this is a piecewise function here. So we're going to say it's going to be equal to g, oops, sorry. It's going to be equal to g plus h as long as g is less than h. And it's going to be equal to, and now this maybe look a little bit complicated, but we just need to make these curves meet because they need to be contiguous. So we have to do a 1 over w weighting function. And then I'm actually going to get weighted a star here. So g plus, my weight is going to be 2w minus 1 times h. And this is for g greater than or equal to h. Okay. And we have some conditions here on the right-hand side. So they're up here. And we want to check these conditions again. And so what we see is there's 2 parts. So there's actually one other thing we should verify, is we should verify that the points meet. But if we look at point 1, what we can see as I increase g or h, then obviously g plus h gets bigger. So that's fine. And we see that both on the left-hand side and the right-hand side. Again, there's some conditions on w not being too small, like not being 0, but we're not going to, well, that'll come out later. Then we can think about, well, what if I increase h versus increasing g? And you see in the first one, in this first part right here, they're both going to be equal. So we're going to hit the equality condition here for number 3. And for the second part, when we're looking at this down here, what we can see is that when I increase my heuristic, which is, sorry, my heuristic is x. So when I increase my heuristic here, it needs to get bigger. And you see when I increase the heuristic, it's actually got this bigger weight on top of it. So we're going to get that. That's going to be true. So now we can check these. Let's just see that x comma 0 is equal to x. And so again, I'll write these just in blue. And we can check here. So there's 2 things that we need to check. We need to check both when g is less than h and when g is greater than or equal to h. It should be fairly obvious that when g is equal to 0, then this is just equal to h. Okay, and then the question is, do we have to check the second part here? And actually ends up, so look at this a little more carefully. The question is, where is g is less than h? Where is g greater than or equal to h? And if I just draw out what this curve looks like, the piecewise curve looks something like this, where we have a dividing line here, and on this side of the line we're getting g plus h, and this side of the line we're getting 2w minus 1. And so it actually ends up that you don't have to check both of these, this condition for both of these. So this is where we have to check condition 4, and this is where we have to check condition 5. So if we look at condition 5, then we want, in this case, we're going to say that h is equal to 0. So this whole term is going to go away. And then g is equal to w times g, because that's what our bounding function is here. So g is going to be w times g, and these w's, we're just going to end up with g there. And so that'll work here. Okay, just to write that up, it's not clear. So if I want phi, actually, so we want this to be equal to 0. Our bounding function is going to be w times x. So 0 times w times x should be equal to x. And so if I get 1 over w, g is equal to w times x, plus h is equal to 0. So this is equal to, the w's cancel, is equal to x. So this holds. Okay. And the last thing we need to check is this property here, that if I add delta, then I'm still okay. And we did this check right here, and it ends up that right here, if I add delta to both, I get 2 delta, so I get less than or equal to. That condition is holding. And if I look at this piece right here, what you're going to see is this is essentially equivalent to what's going on here. Because I'm weighting this down, well, let's just go ahead and do it for the exercise of it. So we know it's going to hold for the first part, and we're going to get 1 over W times G is going to be G plus delta plus 2W minus 1 times H plus delta. And then we say minus, and we're going to subtract 1 over W times G, and minus again 1 over W times 2W minus 1 times H. Okay, and if we look carefully here, so I'll go ahead and draw these in red, what we see is there's a 1 minus G over W term here, so that's going to go away. And then what we see is we have a 2W minus 1H right here that is divided by W because there's a W distributed there. So we get a 2W minus 1H divided by W, so that term is going to go away. And what are we left with? So what we're left with here is delta over W plus 2W minus 1 over W times delta. And so we can just, so I had to do that right, yeah, W. So this is going to be equal to 2W, well, there's a couple ways we can do this. We'll just break it up. So I have delta over W plus 2, and the W over W cancels, times delta minus delta over W, and that is going to be equal to 2 delta. So we're okay there. Okay, so this is just a little bit of row algebra here, and we just have to do this to check things out. And let's go ahead and take a look and see what this piecewise XD function looks like. So here's the piecewise XD function. As I described to you, on the right-hand side, we have this line at a 45-degree angle. And below that line, we're using a 45-degree line. Above that is the slope there is 2W minus 1, or 1 minus 2W. But that's where the slope is coming from. And then we can watch and see how the algorithm runs. And I'm not showing exact numbers here. I'm not going to show you numbers, but if we remember what was happening before, we can see that this is actually doing far fewer node expansions. We're getting just a really, really small fraction of what we did previously. Okay, so that's piecewise XD. And we can, there's another version of this, which is, I'm just going to show it to you. I won't do the full check here, but this is piecewise XU. This is just going to be convex upward. Sorry, and just so we can highlight here what is actually our phi function. Okay, the phi function here is going to be similar to what we did. So piecewise XD, what it did is we had optimal, and then we had suboptimal. And what we're going to do here is we're going to reverse this. We're going to do the suboptimal portion first, and then we're going to do the optimal portion after that. Okay, so let's look at how that works. So this is a slightly more complicated bounding function. So I'm going to go back to using black here. So phi of h comma g. And what is this going to be equal to? So we're going to have g over 2w minus 1 plus h in the case that g is less than 2w minus 1 times h. And we're going to get 1 over w times g plus h in the case that g is greater than or equal to 2w minus 1 times h. Okay. And this is where we see that a 2w1 pops up here and seems to be fairly important. Like for instance here, just pointing out here, we ended up with exactly 2 delta there. And so we're basically exactly what we can be. If we tried to get something that was steeper, then here we're more than 2w minus 1, then we'd be getting in trouble because we'd be increasing this delta to be larger. Okay, so if we look at this, I'm going to go through this relatively quickly because, as I said, now the math is hopefully it's getting a little bit rote, but we can check, for instance, that when g is equal to 0, I'm just left with h there. When we think about our bounding function, so if h is 0 and g is w times my solution, then that division by w is going to meet that. So if I go back up here, then we get both conditions 4 and 5 there. These conditions, what we see is that these two pieces, as before, so let me go ahead and draw them. The two pieces we have here, what we have is something like this, where this is 2w minus 1, and this is optimal. And so what we'd find out, of course, is we'd get, because this is 2w minus 1, we'll get the same, like the same 2 delta there. And so this works, or is going to work. I'm not going to work out all the math there just for succinctness, but it's a good exercise to try that and just make sure that these things are working out. Now, let's go ahead and take a look at what happens when I run piecewise, this piecewise convex upward. And what we're going to see here, so again, this is a curve that I showed you. And if we watch this run, what we're going to see is, at least on this problem, we're going to get much worse performance than we did before. And in fact, here the performance is not much better than actually just running A star. And so what we've seen experimentally is when we get really large weights, then this curve can work okay, but the piecewise convex upward curve does not work nearly as well when we are working with low weights, which is exactly the problem instance that's being run here. And as I said, when I'm done with this analysis here, we'll go ahead and look at that and explain what's going on. Okay, so I want to show you we're going to look at one more potential bound that we can use. And when we're looking at that bound, what we're also going to do is look at like how you can run it and not run it. What works and what doesn't work. Oops, so that's, I want this. So now these up here were all for the bounding function of b of w is equal to w times x. And so down here, what we're going to do is we're going to use b of gamma, which is going to be x plus gamma. And the way we're going to do this, so the first thing that we're going to do, how can we get an additive bound? The first thing that we're going to do is we're going to divide our state space up. We're basically going to run weighted A star underneath this line. And then above the line, we're going to run a, let me try and draw that a little more clearly. Because actually we can do this, here it's very interesting actually, we can use a very, very steep search here. So we're going to set some bound. This line here is going to be k. It says, at what point am I going to switch over from running weighted A star? And then above that line, we're going to run A star. So with A star, we're going to get our sort of x equals y line there. Okay, and so what I can choose is basically I can choose my k, and I also can choose my my gamma, which is my amount of suboptimality. And so my gamma basically says, well, look, if I'm going k, then I have to distribute the suboptimality within these k steps. So I'm basically going to run weighted A star, thinking that it might find something that's suboptimal within my bound, and then I'll resume and switch over to running A star. Okay. And so let's go ahead and look, what is the phi function here? So here we get phi of, again, h comma g. And it's going to be the following piecewise function. So we're going to say k minus gamma over k times g plus h as long as g is less than k. And when g is greater than k, then we get g plus h plus gamma. Okay, and let's go ahead and check our let's check what's going on here. Now, there is something funny that goes on in the corner down here. And we'll look at this in a second. Actually, we'll look at it in a second with a different curve. but we're gonna make some assumptions that we're not sitting in that corner down there. Okay, so what's going on here? So if we think about this, when we are, so we want to check, for instance, does phi of x comma 0 equal to x? And that's always going to happen in the bottom part of this curve. And when g is equal to 0, then I get h back out. So phi of x comma 0 is always, so in this case, that's g is always going to be 0. Get this portion right here, and I get h. And then if I think about my bounding function, the point that I hit here, is that equal to b of x? And so let's look at the places where I hit it above here. So when I'm greater than k, well, I get g plus h plus gamma here, and so that's exactly bounded by my additive bounding function. Okay, so that is being verified there. And the other thing we'll want to verify, so we can see that these pieces of slope, if we look at the slope, then this looks exactly like our weighted A star, and k minus gamma here over k is going to be less than 1. So this is okay because weighted A star, just we're using these weighted A star and A star pieces, so they're going to work. But the last thing we should check here is what happens when we go ahead and use this delta. So we're going to check this consistency. And when we check it, if I know for this piece down here, obviously this is going to hold, because if I add the delta and then subtract it, I'm just going to end up with exactly 2 delta. So let's look at this case. So here I'm going to have h plus delta, g plus delta, minus phi of hg. And we know that needs to be less than or equal to 2 delta. And we're going to assume that g is less than k. So what do I get here? Well, I'm going to get k minus gamma over k times g minus delta, and plus h minus, that's plus h plus delta. And then I get minus, and I'm going to assume that I'm also down here when I do my delta. And so when I do that, I'm going to get, now I'm just going to get k minus gamma over k times g plus h. And as we saw before, then, this is minus h here. So this term here is going to match up with this portion of this term. This minus h is going to match up with this term right here. And what we're going to be left with is k minus gamma over k times delta plus delta. And since, as I said just a second ago, this term right here is, we're going to assume that k is greater than gamma, then this term is going to be less than 1, and therefore we're going to end up with being less than 2 delta here. Okay, so that's great. It gives us an additive bound by running weighted A star for some portion of time. And as I didn't check them all directly, but we've seen that all of the 6 conditions that we needed to hold will still hold here. Okay, so now we have this interesting question, which is what happens, so what happens in this corner down here, I'm actually going to draw that out in a second, and what happens for that and what happens here is somewhat similar. And so how are we going to do this? So I guess the first thing let's do, actually, let's look at a video of how this runs. Okay, so here's this function. We've called this phi of AB. And we can see here we have some line. This is the purple line here is this place where I'm going to switch over from running weighted A star to running A star. And that's, well, this is partially determined. The slope of the line here and the location of the line is determined by the additive suboptimality bound. And so when we run here, we see the search going on. And if we look at the behavior here, the behavior isn't necessarily fantastic. And if we look at this curve, it actually resembles a little bit the curve that we had before when we were thinking about our piecewise convex upward curve. So the piecewise convex upward curve, instead of having a horizontal line, had a diagonal line. But it resembles this at some high level where we're doing suboptimal at the beginning and optimal at the end. And so we might ask the question, can we do something different where I'm going to do optimal at the beginning and suboptimal at the end? So let's take a look at that and see what a phi function would be that would do that for us. And let's see what happens. So what we want here is what we want to do is get something, and let me draw out what's going to happen here. So what we want is this. Sorry, we'll go back to our black lines here. Okay, we want something that looks like this, where I'm going to have some transition points. And on this side of the transition point, we're going to run exactly at 45-degree angles, because that's going to give us A star. And over here, what we're going to do is we're going to run something that's just a little bit steeper. Okay. So we've got a steeper curve over here, and the idea is that within this range, so this is a sort of equivalent. Here we're going to call this B. This is what we call it in the paper. And so B is our going to crossover line where we're suddenly going to get a bunch steeper. And then what the slope that we get in here depends on our value for gamma. So what is our phi function? Our phi function here is going to be this, if we tried to get this. So phi of h comma g is equal to g plus b plus gamma over b times h minus gamma, as long as h is less than b. And g plus h in the case that h is greater than or equal to b. So so this is our b line right here. If we're greater than that line on this axis, then in this case we're just doing a star. And if we're below this line, then what are we doing here? Well, this is g plus some w times h minus a constant. And essentially what this does is this weights it up and then subtracts it back down. And we'll take a look at what happens here. So we could validate this, and we could say, and we can validate the different checks that we want to do. So one thing I'm going to show you, and let's just draw this here. If we think about here in this little corner down here, and let's just think that, so we're going to set this up essentially so that the weight here that we're using here is going to be a factor of 2. So for instance, we could assume that for instance b is equal to 3 and gamma is equal to 3, then we're going to get this equivalent weight of 2. And so what should happen here? Well, what should happen is that when I go from this point that's on exactly at this crossover point for b, then instead of going straight up, what I'm going to do is, so if this is, let's just say this is 3, because that's what b is here, and then this is 3 here, I'm allowed to be suboptimal, so I'm actually going to be allowed to be up here at 6. Okay, so maybe my lines, my lines won't be consistent between this figure. Okay, so let's actually make another figure just to make sure that we can be consistent. Okay, so we're going to have a crossing point here of 3. We've got this 3. We've got a 3 here, and we've got a 6 here. Okay, and what's going to happen on this problem? So right here, what we're going to get is we're going to get a slope of 2. And that's going to take us right up to 6. And if we think about all these points where I hit here, and if I hit at a point, so if this is 1, I go 1 here, then what this is going to do is this 1 is going to go right up here to 7. And so as I cross this point one step higher, I'm going to cross up on top. Right, across here higher, I'm going to cross up here higher, and these lines are going to correspond to each other. But what happens when I go here? So if I get to 2, what's actually happening is I'm using weighted A star with a weight of 2. So actually 2 is going to connect to 4 right here. But with my additive bound, what I really want to have happen is I want to have 2 connect to 5. Okay, so there's a discrepancy in this corner, basically in this piece down here, where I'm sitting just underneath this first line, underneath the first line that connects right here. We suddenly, our lines aren't going to connect, and we're not going to actually have the values that we want there. Yeah, so inside here, our different conditions will not hold. And actually, it would be the same thing if we look up here. So inside here, we're trying to do some additive thing, but we're going to still have some problems down here. So we have to be a little bit careful about that corner, but we can avoid it. if we need to. Okay. But there's a bigger problem that's going on here, and we can actually see this a little bit visually of what's happening. And what we see happening here is basically we have these lines that are equally spaced with each other, but when the slope gets steeper right here, these lines are going to start getting closer together. Okay. And so let's go ahead and we'll check our different conditions. So for instance, we want to ask here, do the curves meet at, so here I want to check for this crossing point. What if h equals b? So if I say phi of b, g, I do want to make sure these lines meet because it's a piecewise function. And so what we're going to get is g plus, and then h is equal to b. So I actually end up with b plus gamma. The h's over the b is going to give me 1 minus gamma. And so that's just g plus b. And down here I get g plus b. So my lines are meeting, and that's great. I can check in the space out here. So we're just beyond this b line. As I said, it was problematic here. But I can check to see that we get our bounding function out here. And what we can see is, for instance, just using some number here, let's say what is b of 5 comma 0. And if I look at this, then h is equal to 5, g is equal to 0, and in this case we had a weight of 2. So h of 5, 0. Sorry, what am I looking at here? So h is, to be careful. Okay, h, so what is h? H is equal to 5, h is greater than b, so we're going to be actually running this one. 5, 0 is going to be equal to 5. Now, the other thing that I can be looking at is phi of 0, comma, my bounding function of 5. And in this case, it's going to be phi of 0, comma, the bounding function of 5. My suboptimality is 3, so that gives me 0 of 8. And so now what I have is, we're going to look at what the value that I get here. So what is h? H is 0, so h is less than b. And so what I get is g is 8, h is 0, so this is going to be 0 minus gamma. So just to say we're getting this equation right here. And that's minus 3 is going to be equal to 5. Okay. And so that's correct, the bounding function here, that's working. But let's take a look at what happens here. And in fact, we only have to look in this piece right here, and we actually already did this derivation. What happens when we check for the consistency of the phi function? So what we get is g plus delta plus b plus gamma over b times h plus delta minus gamma. And then we subtract g, we subtract b plus gamma over b times h, and then we add gamma here. And again, looking at these terms, we see the g is going to cancel out here, the gamma is going to cancel out here, the h portion of this term is going to cancel out, and what are we going to be left with? Well, we're left with, that cancels out with this piece here. And so what we're left with is delta plus this portion here. So these combine together, which is b plus gamma over b times delta. And in this case, this term is greater than 1. And so we're asking, is this greater than or equal to, or less than or equal to 2 delta? And the answer here is no. This doesn't hold. So what's happened is that when we switched from this portion of the space over here to this portion, we've pushed all these curves to be closer than each other, and we've violated this consistency of the phi function. And so we're not allowed to, we may not get bounded suboptimal solutions if we don't reopen nodes in this part of the state space. Okay, so I can't run that and show it to you. I mean, I could run it and show it to you, and it's going to produce some results, but there are problem instances where then this wouldn't return a bounded solution. So now what I want to do is the last thing to finish off this portion of the lecture. And I realize this has been long and a little bit of detail, but going through these details, making sure that you can do these is the way that we are going to be able to create our own phi functions. And I would encourage you again to look at this paper from 2021. It proposes some other phi functions as well that I'm not going to talk about here, but let's just talk about intuitively what's going on. So there's actually some really interesting things we can notice, particularly about our different phi functions. So we're going to look here at xdp, where I'm searching optimally for some portion and then suboptimally above that. I'm not very good at getting these slopes to look very good here, and let's really make these suboptimal. It's going to go way up there. I guess my problem is my midpoint line isn't exactly diagonal, but and we can compare, and so we can think about, okay, let me try and make this, I'll try one more time. So here's my curve. I'm going to use the line function in here to try and get that to be as diagonal as possible. And now I'm going to take something like this, and we're going to really be steep here. So give myself a target to draw to, and we get something like that. And this is to be compared with, for instance, what does weighted A star do? So weighted A star is going to draw a line there. And the important thing is, if we zoom in here, is that there is this gap inside here. And so we can use this to make a geometric interpretation of what is going on here. And we're going to start with the assumption. Now, this assumption isn't necessarily true, but we're going to assume that both weighted A star and piecewise XD are finding a solution of exactly the same cost right here. Then we have to ask, when we run these algorithms, what nodes do they have to expand? Well, the nodes that have to be expanded are the nodes that are underneath these curves. So under here are the nodes that have to be expanded by piecewise XD. And as we said, so weighted A star is going to have to expand the red states, which are inside here, and all the blue states that are inside here. So if all things were equal, if I was finding exactly the exact same solution, then we would see that this piecewise XD curve would dominate weighted A star and would be able to always find, would always use less nodes to find the same quality solution. Now in practice, this isn't true. There's a couple things that complicate that. So what complicates that? One thing that happens is that we may find different solutions, and so now like I have two different lines overlaid on each other, and that may cause things to look a little bit different. The other thing though that can happen here is that when we actually search, and you can see this in some of our search demos, these curves actually, because the F cost, or because the phi cost is allowed to go down, it's not allowed to, the consistency of the phi says we can bound how much it goes down, but it still can go down. And so what can happen is basically these curves, if we think about like the best state, these curves go up and down during the search. And that means that, depending on the order in which I search states, these curves can drop down or go back up again. And let me just, I'm going to show this on our constant graph here that we were looking at just a minute ago. But if we just watch what's going on here, we can see this on the right-hand side that is bouncing up and down a little bit. And so that's basically, well, we had to go to a higher phi value, and then we drop to a lower one, and then we go back to a higher one, and we go back to a lower one. So while in A star, the values just consistently increase, in a function like this, they drop and go up and drop and go up. Okay, so that means that we can't directly predict what's going to happen. There is actually some nice theory on this that sort of tries to explain on a particular problem how much work you're going to have to do. But we're not going to talk about that here. So, okay, so if we were to find the same quality solution, then we would see that piecewise XD would dominate weighted A star. But let's go back here. So that's one observation that we can make. There's another observation we can make which is somewhat interesting here, and that's looking right here. So what we notice here, if we run piecewise XD, that the first portion of this curve right here actually is totally independent of W. So no matter what W is, you're going to always do exactly the same number of nodes. That is, you're going to search optimally until the G cost is greater than the H cost. And at that point now, I get to start searching suboptimally. And so one thing we've hypothesized is that, and there's more work that needs to be done to understand this, but is that looking at this, what is the number of states that have G less than H? If there's a lot of states with G less than H, then we may pay some overhead to search all of those. But if there's not very many states like that, then this is going to be really good because we basically are going to get to use this 2W suboptimality everywhere or almost everywhere as long as the number of states with G plus H is small. Okay. Now, there's other curves that we can use. Just to mention in the paper, we can look at some ways where we can do something like this, where I'm searching optimally at the beginning, optimally at the end, and we can do some suboptimality in between. And so this is interesting because something like this can target one area of the state space and say, you know, whatever, some fraction of the state space here is where we're going to be suboptimal. And here we're going to be optimal on both the top and the bottom. So that's interesting, and there's some general curves like that you can do. And you know, there's many other things that might be possible to do here. We've really opened, the space is open, and nobody really knows how well this could be exploited by other algorithms, by other approaches. But we do have, so just going back here, you know, we just have these conditions here. And as long as we meet these conditions, now we can search without doing re-expansions. And so I think, at least research-wise, there's really interesting questions of what's going to come out of this. Where can this be applied? Where can this maybe in unique applications or in other contexts that maybe we can get some surprisingly good results elsewhere. So that's the end of this video, and hopefully this is useful for getting a feeling of what these phi functions are doing, how we validate what these phi functions do. And after this, we're now going to move away from suboptimal search, and we're going to move to bidirectional search. So that'll be in the next video.